Hi everyone, welcome along. We are looking at projectiles. We're going to start off with this question 5. If you're looking at fundamental applied maths, that's on page 42. Don't worry about it if you're not. So this is projectiles on the flat as opposed to on the inclined plane, which we'll see in another chapter, which just means that everything is flat. It makes life a bit easier. A projectile is something that just when you throw it or you fire it, and it's fired from a point on the horizontal plane with this initial velocity 10I 49J, I'll explain in a second, meters per second. Find its greatest height, its range, and its velocity as a vector after 6 seconds. So here's the setup you're looking at. Something is fired in such a way that it has a velocity of 10I and 49J, means 10 meters per second going across, okay, in a horizontal direction, and 49 meters per second going upward. So it's fired this way, but it immediately will start to fall under gravity so that it follows a path or a trajectory that looks like this. Okay, and this question has asked us two things. It's asked us to find its greatest height and also to find its range, okay, which is this distance here. There's a third part of the question then that asks, that we'll come to in just a second. Now, with range and greatest height, you're going to be asked over the next chapter, you're going to be asked that again and again. Find the range, find the greatest height. Greatest height, they both have conditions attached to them, okay? And our condition for greatest height is that our velocity in what's called the J direction, or in the vertical direction, needs to be 0. So if you can imagine this 49, as it fires upwards, it slows down under gravity. By the time it reaches this greatest point here, it stopped moving in the J direction, in the upwards direction. So that's our condition for greatest height. And we're going to use that again and again. So I'm going to say, learn that off by heart, please. Our condition for range is, well, what happens if you look at the distance traveled in the J direction, okay, excuse me, the displacement, you'll see that it gets bigger and bigger and bigger. Okay, as you move across, you get higher and higher and higher, but then you start dropping back down. By the time you get here, your displacement in this direction, in the J direction, you've landed back where you started. In the I direction, you've moved, okay, across, but in the up-down direction, you've landed back at your starting point. So our range, our condition for range is where the displacement in the J direction equals 0, and then it is, what is the displacement in the I direction? That's our range. The displacement in the I direction while the displacement in the J direction equals 0. Now, setting these questions up, well, they've told us what we do, is we look at our usual UVAS that we've seen for linear motion, but now we do it twice. Okay, what we find is that motion in this direction is independent, does not depend on motion in this direction. So we can treat them as two completely separate problems and then put them together at the end. So here we're told, well, we start off moving across at 10 meters per second. We start off moving upwards at 49 meters per second. Okay, the V's we'll talk about at a later point. That's changing the whole time. The acceleration, well, the only acceleration acting here is gravity, which acts downwards, so we give it a negative sign, and it always has a value of 9.8 meters per second squared. Okay, so that's gravity acting downwards. The last thing we can fill in here is say that the time for the particle, whether you're talking about the time it's been traveling left, right, or the time it's been traveling up, down, is the same. So we can say T and T here are the same. Okay, I can also say that in its travels across, the acceleration is 0. There's nothing causing it to speed up or slow down the projectile in the I direction going across. And some of you might recognize there we're ignoring things like wind resistance. Okay, so the question is, 1, find the greatest height. So you come along and you say, well, what's my condition? Well, it's when my velocity in the J direction equals 0. Okay, that's when I'm at my greatest height. I've stopped moving in the upwards direction, but I haven't yet started moving downwards. So my velocity in the J direction equals 0. Well, looking at that, V equals U plus, I'm going to change that to a minus because it's minus AT, U plus AT. Okay, there's our general velocity at any given time t. The initial velocity plus the acceleration times time. And the acceleration is negative, so I'm making that a negative. So you let that equal 0 to find the time at which you're at your greatest height. 9.8 t equals 0. And solving that, move that 9.8 minus 9.8 across, because plus 9.8, and dividing through by 9.8, 4.9 divided by 9.8 is 5. Okay, so what we see here is that after 5 seconds, we're at our greatest height. I divided through there by 9.8. Now, what I should have said here was that the velocity in the j direction equals 0, but what we want is the displacement in the j direction. So let's find the displacement in the j direction when the velocity in the j direction is 0. So you're going to say, if t is 5 seconds, what's my displacement in the j direction? Well, again, a general formula, ut plus half at squared, is 49t minus 9.8. I'm changing that plus to a minus because it's a minus 9.8, half of the acceleration times t squared. There's a general expression for the distance. So now we say, well, when t is 5, that becomes 49 times 5 minus 9.8 over 2 multiplied by 5 squared. And you get there 245 minus 122.5, which gives us 122.5 meters. That's our maximum height there, 122.5 meters. And it occurred, that was the displacement in the j direction when the velocity in the j direction was 0. Part 2 asks us to find the range of the particle, that is this distance along here. Okay, and our condition for that is displacement in the j direction, displacement in the I direction when the displacement in the j direction equals 0. Okay, so let's go over that again. You're going up, 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 up to here, and then from here on you're going down, 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 down. But your displacement right at the end when you land here in this direction, the j direction equals 0. So we let that be our condition. Displacement in the j direction equals 0. Well, here it is here. 49t minus half 9.8 is 4.9t squared equals 0. You might spot a common factor of 4.9. I'm going to divide through. I get 10t minus t squared, 1t squared equals 0. And then factorizing that, t times 10 minus t equals 0. My two solutions are t equals 0 or 10 minus t equals 0. So t equals 10 seconds. No surprises there. On flat ground, the time it takes to get halfway, which is to its maximum height, is always half of the time it takes to get to the ground. But these conditions are important for later on when we move on to slanted ground. Now that's only part of it. The question was find the range, not find the time it takes to land. So the distance traveled in that is displacement in the I direction after 10 seconds. So our general formula here, S equals ut plus half at squared, becomes just 10t, but plus a half of 0 times anything is 0. So it's just 10t. Okay, so displacement in the I direction is going to be 10t, which is 10 times 10. That's 100 meters. So for this projectile, it's traveled 122.5 meters in height. And by the time it lands, it's traveled 100 meters, okay, across. So that is maximum height and range. Those are really, really common questions. The last part of the question now, part 3, asks it for its velocity as a vector after 6 seconds. So what do they mean by that? So we know that this happens here. Its highest point is after 5 seconds. So it's 6 seconds, maybe it's here. Okay, it's traveling in this direction. That's its velocity. But as a vector, they want to know what is its I and j component. Okay, and just straight away from my diagram, you probably see I will still be positive. In fact, I doesn't change when you're along flat ground. So it's still going to be 10. I'll show you why now in a second. Its downwards component, because it's downwards, will be a negative. Okay, so what they're looking for there is this v with the arrow on the top means the velocity as a vector at t seconds. Well, the velocity in the I direction, okay, to come back here, v equals u plus a t, well, that's going to be 10 plus 0. So that's why that never changes, okay? Velocity in the I direction is still 10 meters per second, just like it was at the start. The velocity in the j direction is 49 minus 9.8 t. Okay, which for us after 6 seconds is 49 minus 9.8 times 6. which when you go to your calculator and work it out, 9.8 times 6 is 58.8. Subtract them, it's 9.8 meters per second. That, by the way, has nothing to do with gravity. It's purely a coincidence that we get minus 9.8 there. But that's the velocity in the j direction. So the velocity that they're asking for after 6 seconds is still 10 in the I direction, minus 9.8 in the j direction with the unit of meters per second. So that's the answer to part 3 there. Okay, so all 3 parts of this question are really, really standard. In fact, most of the exercises asking for the same type of thing over and over. So what I'm going to ask you to do is go back and have a look at this question, question 2, and give that a go yourself. It's almost identical. I think you should be able to manage it just fine. Okay, and I'll see you tomorrow. Bye-bye.